ViewBirdification is the task of recovering ground plane movements of the observer and pedestrians just from an ego-centric video of people in a crowd. This opens a new use of ego-centric videos, for dynamic surveillance, localization, and planning. Prior work iteratively estimates the on-ground ego motion and pedestrian trajectories by constraining them with a predetermined crowd motion model. This is computationally expensive and the application is quite limited due to its slow execution time and predetermined motion models. We propose ViewBirdiformer, a novel transformer network that estimates both the ego motion and the pedestrian trajectories with a single inference pass, without making restrictive assumptions on their interactions. ViewBirdiformer achieves joint recovery of the ego motion and pedestrian trajectories, which opens the door to accurate real-time, always-on situational awareness. The key challenge of this data-driven ViewBirdification lies in the joint recovery of ego motion and pedestrian trajectories while learning its underlying motion models. Further, the input is 2D in-image movements relative to ego motion, but the expected outputs are on-ground trajectories in absolute coordinates. We address these challenges through cross-attention between views using relative transforms and modeling crowd motion with self-attention. Our unified transformer architecture enables joint recovery of the ego motion and the pedestrian trajectories in a single inference pass, which bring us significant improvement in the execution time. ViewBirdiformer consists of three main components. First, an in-image pedestrian state encoder that encodes pedestrian movements in an ego-centric view. Second, an on-ground past trajectory encoder that implicitly learns the crowd motion. And finally, a cross-view attention block that decodes on-ground trajectories from it. To achieve simultaneous recovery of pedestrian trajectories and ego motion of an observation camera, we formulate birdification as a multitask learning problem. The output embeddings consist of two types of features, an ego motion embedding and pedestrian trajectory embeddings. We define individual loss functions for these two tasks. To make the network generalize over diverse combinations of trajectories and observer positions, we transform all on-ground pedestrian queries relative to the previous camera pose estimates. Using the intrinsic matrix, we can compare the reprojection and the observation in the image plane. The reprojection loss provides a powerful inductive bias for on-ground trajectory estimates. This can be used as a soft geometric constraint in the weighted loss function at the training phase, and as a hard geometric constraint at test time. While the original ViewBirdiformer outputs achieves sufficient accuracy, the reprojection loss can be used to further refine the ego motion towards the pedestrian trajectory estimates in test time. The camera pose estimates are refined to minimize the reprojection errors. Following Nishimura et al., we create a large-scale ViewBirdification dataset consisting of paired real pedestrian trajectories and synthetic ego views to train and test ViewBirdiformer. Our transformer architecture enables estimation of both ego motion and pedestrian trajectories with a single inference pass, and it results in 3 orders of magnitude reduction in execution time over an iterative approach, even including geometric post-processing. Here are the qualitative results. Our method successfully reconstructs on-ground movements of both the observer and the surrounding people, and can be generalized to crowds of different densities. We also show the attention weights in the multi-head attention layers of ViewBirdiformer which encode the pedestrian interactions. In cross-attention between the ego-centric view and the on-ground trajectories, our model adaptively attends to both the ego-centric view and the on-ground past trajectories to better predict the next steps conditioned on the ego-centric movements. Furthermore, we tested our pre-trained model on the real video picked up from 2D multi-object tracking dataset including ego motion. Since ViewBirdiformer takes not the raw image, but the sizes of detected bounding boxes and their displacements as inputs, the models trained with synthetic ego views can easily be adopted to the real image data. In this paper, we introduced ViewBirdiformer, a transformer network that simultaneously estimates both the ego motion and the pedestrian trajectories with a single inference pass. We believe ViewBirdiformer finds use in various applications of crowd modeling and synthesis across a wide range of disciplines.